Good morning, everyone. Uh, we have defined lifting of a map, and we have proved that whenever we have a covering map P from a space E to B, then any path F in space B, that is, F is a mapping from the closed interval 0, 1 to B, that has a unique lifting in space E. If P is a covering map, then any path F in B, which is starting at point B naught, it has a unique lifting starting at unique lifting F curl, which is a path in space E, and it starts at point E naught in E, where this point E naught is a point whose image is B naught under this mapping P. Similarly, we also have proved if we have a mapping capital F from I cross I to B, and this is a continuous mapping in space B, then it also has a unique lifting F curl in space E. And if F maps the point 0, 0 to point B naught, then this F curl maps 0, 0 to point E naught. This is also unique lifting of capital F. And if this capital F is a path homotopy, then this F curl, that is also a path homotopy. Further, we have also proved that if F and G are any two paths in space B, which are homotopic to each other, then their corresponding liftings, F curl and G curl, they are also path homotopic in space E. And if these two paths F and G starts at point B naught, then F curl and G curl, they are paths starting at E naught and they end at same point. They will end at same point and they are homotopic to each other. So now we define corresponding to these, we define now lifting correspondence. Now, what is lifting correspondence? Now, suppose P is a covering map from E to B, and we choose a point B naught in space B. Let B naught is in B. Then we choose a point E naught such that image of this E naught is B naught. Means we choose a point E naught in the inverse image of B naught. And then for any element path homotopy class F of this group pi 1 B B naught, the fundamental group of the space B with respect to B naught. Now, since this is any element of this group, so it means F is a path in space B starting at point B naught, based at point B naught, in fact. So we can assume the unique lifting of this path in space E, which begins at E naught. So let F curl be lifting of F in space E beginning at point E naught. Then we define a mapping phi from pi 1 B B naught to P inverse B naught by this phi of path homotopy class of F, that will be equal to F curl at 1. That will be F curl 1. Because we know F curl is a path in space E which starts at E naught, and F curl 1, this is end point of this path. F curl, and that is a point of space E. And in fact, that belongs to P inverse B naught, because we know F is a path. F is a path based at point B naught, and we have already proved that if F is a path based at point B naught, then its lifting F curl, that will be a path whose endpoint should be E naught. And sorry, endpoint should be inverse image of point B naught, and that we will take as the image of this path homotopy class of F under the mapping phi. Now we will call this phi mapping the lifting correspondence derived from the covering map P. So we call phi the lifting correspondence which is derived from covering map P. This mapping phi is well defined because F curl 1, that is endpoint of the path F curl, and that is actually inverse image of B naught. So this lifting correspondence depends, of course, on the choice of the point E naught. Now in this, now in next theorem, we will prove that this lifting correspondence is surjective if the space E is path connected, and if the space E is simply connected, then it is bijective. So we will prove in this theorem, if P is a covering map from E to B, and under this mapping E naught goes to point B naught, then if E is path connected space, then the lifting correspondence mapping phi is surjective. And if E is simply connected, then it is bijective. So let us prove this theorem. If E is path connected space, then the point E1, take any point E1 which is an inverse image of B naught. Since it is path connected space, so there is always a path F curl from E naught to E1. So if we take any point E1 in inverse image of B naught, since this is a path connected space, there is a path. Let us say that path is F curl. Let F curl be a path in E from point E naught to E1. And then we define mapping F to be the composition P circle F curl, because F curl is a path in E, so it is a mapping from I to E, and P is a mapping from E to B, so this composition is well defined. And secondly, F curl is a path from E naught to E1, and P of E naught is B naught, and secondly, P of E1, that is also B naught. So this composition is actually a path in space B, which is a closed path based at B naught. So this F will be a loop in space B based at point B naught. And then image of path homotopy class of F under phi, by definition of phi, it is F curl at 1, and F curl at 1 is E1, because E1 is the ending point of the path F curl. And now from here we can say this F is a path in space B based at B naught. That means a path homotopy class of F belongs to the fundamental group of B with respect to B naught. And if F is equal to P circle F curl, that means F curl is a lifting of path F. And we know every path has a unique lifting. So this F curl is the unique lifting of F, which is starting at point E naught. So by definition of lifting correspondence, phi of F, it is F curl at 1 means end point of the unique lifting of the path F starting at point E naught. So that will be E1. So we have proved here that for any point E1 in P inverse B naught, there is path F, there is a loop F in B based at B naught such that such that image of this path homotopy class of F, that is E1. So this phi is surjective map. Now we come to second part of the theorem. Now we want to prove if E is simply connected, then it is bijective map. Now if E is simply connected space, then we have to prove this is bijective map. So we will assume here that we have two different elements F and G of phi 1 BB naught such that their images are same. Phi of F is equal to phi of G. So now we want to prove that F and G basically they are same elements, they are equal. That means we want to prove F and G are homotopic to each other, path homotopic to each other. So phi of F is equal to phi of G means F curl at 1 is equal to G curl at 1, where F curl and G curl, they are liftings of paths F and G in space E which begin at point E naught. Now E is simply connected space. So there is a path homotopy in space E between F curl and G curl, because F curl and G curl both are paths which are liftings of F and G starting at point E naught. So their starting points are same. And secondly, we have proved now here F curl 1 is equal to G curl 1, which means they have same endpoints. And we know whenever the space is simply connected, then any two paths which start and end at same points, they are homotopic to each other. Therefore, this F curl and G curl, they are path homotopic to each other. So if these two are path homotopic to each other, then these two compositions, they are also path homotopic, and the compositions are equal to basically F and G. So F and G are path homotopic to each other, which means the path homotopy class of F is equal to path homotopy class of G. So the mapping phi is 1-1 mapping. So this completes the proof that phi is bijective map. So now we will prove that the fundamental group of circle is isomorphic to additive group of integers. So this is our main result. This result proves that fundamental group of circle is isomorphic to the group Z of all group Z, which is additive group of integers. So we will now prove here that fundamental group pi 1 S1 circle with respect to any point, say point B naught, any point of the circle, this is isomorphic to Z, additive group Z. So let us prove this. Now we will take the covering map P from R to S1, which is defined by P of X is equal to cos 2 pi x sine 2 pi x. which we have already proved that this is a covering map. Now we take the point E naught to be point 0. E naught to be the point 0 of this real number, real space R. E naught is a point 0, 0 of this real line. And we take B naught to be the image of E naught. So it means under this mapping Px, which is cos 2 pi x sine 2 pi x, basically this B naught is the point 1, 0 on the circle S1. So now we take P inverse B naught. Now P inverse B naught is inverse image of the point 1, 0. Now because of this mapping, we can see that inverse image of B naught that contains all the integers. So this is set of all integers. Now we know R is simply connected space. So it means the lifting correspondence phi from pi 1 S1 B naught to Z. This is bijective map. Pi 1 S1 B naught to basically P inverse B naught, and P inverse B naught, this is basically Z, set of all integers. So this is bijective map. Now we want to prove that this phi is a homomorphism, because if we prove that phi is a homomorphism, then basically phi is isomorphism, because since it is bijective map. And we want to prove that fundamental group of S1 that is isomorphic to Z, that means we want to prove phi is isomorphism. So we want to prove phi is homomorphism now. Now let us take any two elements, path homotopy class of F and path homotopy class of G in pi 1 B B naught. Sorry, pi 1 S1 B naught. Pi 1 S1 B naught. And now we are assuming basically that F and G are paths, are closed paths in space S1 based at point B naught, and we assume that F curl and G curl, these are their respective liftings to paths in R. Which starts at point 0, because here we are assuming that our E naught is 0. So we assume that F curl and G curl, these are unique liftings of F and G, which begin at point 0. And let us say N is ending point of F curl and M is end point of G curl. Then by definition of lifting correspondence, phi of F is N and phi of G is M. Now suppose G double curl, this is the path which is defined by N plus G curl. That is G double curl at any point S, that is given by N plus G curl at S. Now let us say this be any path on space R. This is any path defined in space R. Now we know P of N plus X, this is P of X, because the mapping P is defined by P of X is cos 2 pi X sin 2 pi X. So P of N plus X is equal to Px for all X belonging to R. Therefore, this G double curl, this is also a lifting of G. This is lifting of G because P circle G double curl at point S. This is P of N plus G curl S, and we know P of N plus X, that is simply Px. So it is P of G curl S, and G curl is already a lifting of G, so it is G of S. So P circle G double curl, this is equal to G. So this G double curl, this is also a lifting of G. But G double curl at 0, this is basically n plus G curl at 0, and and starting point of G curl is 0. So this G curl at 0, this is 0. So it is n plus 0 is equal to n. It means starting point of G double curl, that is n. So we are saying here G double curl is a lifting of G which starts at point n. It means now F curl is a path from 0 to n, and G double curl, this is a path starting at n. It means F curl star G double curl, this is a well-defined product of paths. And F curl is a lifting of F, and G double curl is a lifting of G. So F curl star G double curl, this is a lifting of F star G. And this is a lifting which starts at 0. And the end point of this path is same as the end point of G double curl, and end point of G double curl is n plus G curl at 1. So it is n plus m. So we are saying that F curl star G double curl, this is a lifting of F star G that begins at 0. And we know liftings are unique. So phi of F star G, this is basically phi of F star G, and it will be end point of the lifting of F star G, which is beginning at 0. So this is basically by definition F curl star G double curl at point 1, and that is equal to n plus m, and n plus m is basically phi of F plus phi of G. So we have proved here that phi of F star G is equal to phi of F plus phi of G. So phi is a homomorphism. And since it is a bijection map already, so it is isomorphism. So this proves that fundamental group of circle, that is isomorphic to the additive group of integers Z.